In this video, we're going to be looking at topic 17C, focusing on how the transition metals can be used as catalysts, and this is part of the IAL chemistry course from Edexcel. So there are two different types of catalysts that we're going to be focusing on, that is heterogeneous and homogeneous catalysts. We will be looking at what these two mean and then looking at specific reactions of each of them. So looking specifically at catalytic converters, as well as how vanadium acts as a catalyst in the contact process, and the iron and thiosulfate reaction, and looking at autocatalysis to finish off. So what is a catalyst? Well, you've learned varying different explanations of catalysts. You initially learned back in GCSE that a catalyst is a substance that increases the rate of reaction but remains chemically unchanged. In topic 9 of year 12, you would have learned that a little bit more detail that catalysts provide an alternative reaction pathway, and it's very important that we understand it's an alternative pathway that is a lower activation energy. And you showed this using a Maxwell-Boltzmann distribution curve. If you can't remember how to do that, you might want to go back and have a look at the topic 9 video. So we're going to go into looking at the different types of catalysts and how they actually react, as well as looking at very specific reactions. So a heterogeneous catalyst is one that is in a different phase to that of the reactants, and typically it is that the catalyst is a solid and the reactants are aqueous or gases. And the most common heterogeneous catalyst that you've probably come across will be iron in the Haber process. So the Haber process being the formation of ammonia. And this requires an iron catalyst. Now, transition metals are very commonly used as catalysts in lots of different types of reactions, and the reason that we use them as catalysts is because they can easily change their oxidation state. It only requires a very small amount of energy to change the oxidation state of a transition metal, so they can react as catalysts very easily, because that is the whole purpose of what happens. We get a change in oxidation state, and we will look at this in more detail. Now, the reactions that take place for this catalysis always take place at the surface of the transition metal. So we want to have the largest possible surface area, and we do that by using a fine powder, or we have a thin coating of the catalyst on an inert support material. Now, the main process that you're going to have to know that it requires a catalyst is called the contact process, and that is used to form sulfuric acid. Now, you don't need to know the full description of all of the key manufacturing steps because it can be quite complicated. You do, however, need to know a very specific step, and the key part you must know is the conversion of sulfur dioxide to sulfur trioxide. So we have 2 moles of the sulfur dioxide, which is of course a gas, reacting with 1 mole of the oxygen, which is also a gas, and we form 2 moles of the sulfur trioxide. And all of our reactants and products are all in the gaseous state. This happens at a pressure of approximately 2 atmospheres and a temperature around 725 Kelvin. And how this works is that the mixture of gases is passed over this solid catalyst, and the catalyst we use is vanadium 5 oxide, or V2O5. And what you have to be able to do is to explain how this happens. And we talked briefly about this back in previous topics where we were looking at surface absorption theory, and we will look to explain this process using these steps. So heterogeneous catalysts typically work in 3 steps, and you can use the mnemonic HARD to remember them. So H for heterogeneous, A is for absorption, where 1 or more of the reactants become attached onto the catalyst surface. R is for reaction, where the bonds in the adsorbed reactants are weakened and we get the reaction taking place, making the bonds to the new substance. And then the D is for desorption, where the products become detached from the surface and they move off as the new substances. So what would this actually look like? Well, we have our surface of our catalyst, and of course we want it to be the biggest possible surface area. And we get the steps happening. So if we have our reactant that is going to adsorb onto the surface of the catalyst. And that just means it becomes attracted and held in place there. And then your substance that it's going to react with will come close to it. So let's have it as this, and we will colour this one in. So this is our other reactant that is going to approach the initial adsorbed substance. We're going to get a reaction happening on the surface. So we get the bonds between the molecule on the surface weakening, and then it will start to form new bonds here. So this is our reaction. And then we get a desorption happening where our new substances leave the surface of the catalyst. And that is the last step. So we get adsorption onto the surface where they land on an active site of the catalyst, and then they form a bond with the catalyst. This will then weaken the bonds between the molecule itself. The adsorbed substance is then in the correct orientation and get a favourable collision with the other thing that it wants to react with, causing your new product. And then the products are then desorbed away from the active site of the catalyst to then make that open again and allow something else to react. So we have heterogeneous, adsorption, reaction, and desorption. So you could use the acronym HARD to remember that. So if we take that same process and apply it to the contact process, the reaction between the sulfur dioxide and the V2O5 happens in two steps. So the first thing is that the sulfur dioxide adsorbs onto the vanadium 5 oxide's surface. So we have the V2O5 actually reacting on the surface with the SO2. And that gives you a redox reaction, and we form the sulfur trioxide, which desorbs, and that also forms V2O4. So we've lost an oxygen from the vanadium 5 oxide and given it to the sulfur dioxide to make sulfur trioxide. But of course we know that catalysts have to be regenerated, they don't change, so we must do something here, and what happens is the oxygen that would be present in this atmosphere would react with the V2O4 on the surface of the catalyst, and we get another redox reaction happening, and that regenerates it to allow it to then react with something else, another molecule of the sulfur dioxide. So we get the reaction and then the regeneration happening over two steps. And again, it's because we get this adsorption onto the surface, then the reaction, and then desorption. Catalytic converters are another way to use transition metals as catalysts, and it's something that is actually extremely common, found in every single car, and this is to help get rid of the toxic gases or pollution that can be caused by exhaust gases that come into our atmosphere. And because we have more and more cars on the road every single day, that increases the amount of pollution. And the most significant pollutants that come out of our engines are carbon monoxide and nitrogen monoxide. Now, carbon monoxide we've talked about in topic 16, and topic 17 when we talked about the hemoglobin and how it can't be carried, and you may have talked about this in biology as well. So that's of course a toxic gas that could kill people, so we don't want that in our atmosphere. And nitrogen monoxide is easily oxidized in the atmosphere to NO2, and that contributes to the formation of acid rain. So we don't want any of these gases that are formed in our exhaust or in our engines to be coming out into the atmosphere. So a catalytic converter is used to reduce the effect of this, and it is typically made of transition metals such as platinum or rhodium. Now, we don't need to know the chemistry behind it because that's out with the scope of this course, but it works in the same way as the vanadium. It uses this surface adsorption theory. So the fact that it's a heterogeneous catalyst, we get absorption, reaction, desorption. So the molecules of the CO and the NO are adsorbed onto the surface of the catalyst, and they react to form carbon dioxide and nitrogen. Of course, nitrogen being present in our atmosphere already, so that's not a problem. Carbon dioxide is a greenhouse gas, so it's not the best thing for us to have in the atmosphere, but it is much better to have carbon dioxide than it is to have carbon monoxide or nitrogen monoxide. And once we make the carbon dioxide and the nitrogen, they then desorb from the surface. So we get 2 moles of the CO reacting with 2 moles of the NO, and we form 2 moles of CO2 and N2, but following the same surface absorption. So you can see here that we have the carbon monoxide and the nitrogen monoxide plus the oxygen that is of course in the atmosphere, and we can have palladium or platinum or rhodium, and they'll be in and on the surface of aluminium oxide, which would be inert in this case, and you get the nitrogen adsorbing onto the surface and then changing into our nitrogen and our carbon dioxide. The other type of catalyst that we need to know about are called homogeneous catalysts, or homogeneous, however you choose to pronounce it. And this is one that is therefore in the same phase as the reactants. So they will all be aqueous or all be gases. Okay, most of the time they will be gases, but aqueous solutions do exist in terms of a catalyst in a reaction, but they're just a little less common. And the most important key feature of homogeneous catalysis is the formation of an intermediate species, and we can get a specific formula being formed from this. So the reactions that we need to know about will happen in 2 different steps. So if we have this S2O8 2- ion, which is called persulfate or sometimes peroxydisulfate, this acts as an oxidizing agent in its reaction with iodide. So we have S2O8 2- reacting with 2 moles of iodide, and that gives you sulfate and iodine. The problem with this reaction, hopefully you can see right away, is that this is 2 negative ions. And negative ions, of course, repel each other. So at room temperature, this is an extremely slow reaction to the point where it almost doesn't take place. And it's because of this repulsion between these negative ions. So we want to speed this up, and how we do it is we add in some iron 2 ions to act as a catalyst. This, of course, being a positive charge, is more likely to react with one of our 2 reactants, and it will form this intermediate species. And because this is in the aqueous solution, this is an example of homogeneous catalysis. And as I mentioned previously, this reaction will happen in 2 steps. So the Fe2+ that acts as the catalyst will firstly react with the S2O8 2-. And these are opposite charges, so they do not repel each other. This will form your first product, which is the sulfate, and it will form Fe3+. Now, of course, the Fe3+ is not, we've now changed the catalyst, we have to then put it back into the catalyst of Fe2+, and it does that by reacting with the iodide, so the second reactant, and we form iodine and Fe2+ being regenerated. So we start off with the Fe2+ and we end with the Fe2+, and we make our 2 reactants as well. Now the reaction can also be catalyzed by Fe3+ in 2 steps. The only thing that happens in comparison to the last one is that they're just reversed in terms of the 2 reactions. So we have the Fe3+ firstly reacting with the iodide as opposed to the persulfate as it did in the last example. And that makes our first reactant, our first product of iodine plus Fe2+. And then the Fe2+ will react with the S2O8 because of course they're opposite charges, so there's no repulsion happening here. And we make our 2 sulfates and we regenerate our iron catalyst. So the same mechanism, same reactions, just in a different order of the previous mechanism. Now, we also have a process called autocatalysis, and we did talk about this back in topic 11 when we looked at kinetics of reactions. So potassium manganate 7 in acidic conditions can act as an oxidizing agent in a titration reaction, and we talked about those reactions in topic 16. So when we titrate the potassium manganate 7 with ethane dioate acid ions, the equation is as follows. We have got 2 MnO4 minus plus 5 C2O4, 2 minus, plus 16 hydrogens, giving you 2 manganese 2 plus, 5 carbon dioxide, and 8 waters. Now, it's unlikely you will be asked to memorize this. They will most likely give it to you in an exam, but it's important to know that we've got the manganate becoming manganese and the ethane dioate changing into carbon dioxide and water. As with the previous example, both of these species are negatively charged. So when they are negatively charged, the reaction is very slow at room temperature. But what actually happens here is the Mn2 plus ion acts as a catalyst. So as you make more and more of your product, your rate of reaction increases. And this is because we're making the Mn2 plus is acting as a catalyst, speeding up the reaction. And this is what we call autocatalysis, where we have a reaction that is catalyzed by a product of the reaction. So it is essentially catalyzing itself. And if you remember, again, we talked about this back in topic 11, and we can see what actually happens to the rate in terms of the on a graph. So as your reactant concentration starts to fall, the reaction is very slow at the start, and then it will get faster because you have made more of your manganese 2 plus, so that's acting as the catalyst, before it eventually slows back down as you get your reactants being used up and up. And this is an example, as I said, of autocatalysis. So let's finish off by looking at some past paper questions. When it comes to catalyst questions, these tend to be in the multiple choice because it's quite straightforward. The only thing that might be a written question and a slightly larger written question, maybe 2 to 3 marks, is explaining surface adsorption theory. And my best piece of advice for that would be draw a diagram where possible, because drawing the diagram, as I did previously in the video, clearly shows each of the different steps, and then you can use the diagram along with some sentences to be able to explain it. So the 3 questions that we have here in this video are going to be 3 multiple choice. So transition metals often have catalytic properties. The best explanation for this is what? So the transition metals usually have a much larger surface area. Well, that's not necessarily always true. It depends on the transition metal itself. So it's not going to be A. Transition metals readily promote electrons to higher energy levels by absorbing electromagnetic radiation. Whilst this is a true statement, that isn't to do with the catalysis, that's to do with colour. So it can't be that. The relatively small amounts of energy required to change the oxidation state, well, this is our correct answer, because in each of the catalysis reactions that we've seen, the oxidation state of the vanadium or the iron changed. And this is because it only requires a very small amount of energy, because it's not to do with D, which is the ionization energy, because these are already ions. For question 2, we have iron as a suitable catalyst for the reaction of nitrogen with hydrogen to form ammonia. Why is this? Well, the answer is an A, because the iron is not oxidized. For B, it absorbs the reactant molecules. That's likely going to be our correct answer, but let's just check. For D, it does not desorb the product molecules easily. Well, if it doesn't desorb, then it's not going to be a very good catalyst. And D, it forms hydrogen bonds with the ammonia. Well, that's definitely not right because metals do not form hydrogen bonds. So our answer has to be B. And it's because for surface absorption theory, we need the catalyst to be able to adsorb the molecule onto its surface. And then lastly, the conversion of sulfur dioxide to sulfur trioxide is catalyzed by vanadium 5 oxide. And we have the equation here. And the mechanism is most likely to involve what? Well, this is what we've previously looked at, and we looked at the actual explanation, and we had the V2O5 going to V2O4. So we're moving from vanadium 5 to vanadium 4. So we can get rid of C, because C is vanadium 5 to vanadium 6, and so is D, vanadium 5 to vanadium 6. So it can't be those two. So then we have to look at either A or B, and the reduction reaction does not happen using oxygen, because oxygen is not a reducing agent. Oxygen is an oxidizing agent. Of course, it gives oxygen. So therefore, the answer again must be B, because the reduction of the vanadium by the sulfur dioxide to vanadium 4, followed by the oxidation to regenerate the catalyst by oxygen back to vanadium 5. And there you can see the answers and an explanation of why some of them are wrong. That's everything for topic 17C, transition metals as catalysts. If you do have any questions, please feel free to leave a comment below, and we hope to see you back on the channel soon.